Hi, my name is Daniel Kalny. I'm from the Czech Republic, and in the following presentation, I'm going to show a project demonstrating how GA144, a multi-computer chip from Green Arrays, can be applied in the field of digital image processing.
I got motivated to start the project by coincidence. Recently, I watched a documentary on the National Geographic Channel showing the research of Dr. Sheila Nierenberg, professor at the Weill Cornell Medical College, related to a retinal prosthetic device. It caught my attention, and I started wondering whether GA144 could be used for similar image processing applications. As one of the fundamental methods used in digital image processing is convolution filtering, I have chosen implementation of convolution filters in GA144 as a starting point for my experiments. The demo application I'm going to present takes an image as input data. The image is a grayscale bitmap stored in eval board RAM. It is processed with GA144 applying convolution filter, and the output is then displayed on a VGA monitor. These three parts of the application will be described in more detail now. The first thing the demo application does is to store a bitmap image in RAM on the eval board. This is a 2 MB static RAM with 16-bit data bus. The array4th environment provides source code for SRAM cluster, which allows other nodes to read from or write to RAM. The application loads the bitmap into RAM from a host PC using bootstream. In order to show how this is done, let's review briefly the concept of bootstreams. A bootstream is a sequence of 18-bit words, code and data sent to special nodes called boot nodes. These nodes can read and process boot streams. A boot stream is composed of one or more boot frames. Each frame starts with a header and optionally may have a body. A header is composed of 3 words. The first is a completion address. This is the address where the boot node continues execution once the boot frame has been delivered. Next one is a transfer address, the address where the body is to be stored. If the transfer address points to node's RAM, the address is incremented with each word stored. On the other hand, if the transfer address points to a port, the whole body is delivered to that port. The last word of frame header is transfer count. This is the number of words in the body. If the count is 0, then there is no frame body and the execution continues at the completion address directly. In the following example, we show how the SRAM cluster nodes boot. A boot stream built during compilation of array4th code with streamer utility is sent through an async serial line into boot node 708. The stream is processed by the boot node and moves along the boot path until the end of the path is reached. It then loads code into memory of specified nodes in the backward direction. Thus, nodes which form the SRAM cluster are loaded with code and they start executing. When the last word of the frame has been delivered, the nodes on the path cease any activity and the boot node 708 jumps to the completion address, which may instruct the boot node to expect another frame. Notice that memory of the nodes used for delivering the frame remains unaffected. That is because streams move along the path with help of code executing only at ports. This is a very versatile booting mechanism. You can use the same path to boot other nodes. You can also rip up the current path, define another one, and boot nodes elsewhere. A path covering entire chip can be used to boot the whole application at once. As will be shown in the next example, this mechanism is applied to load RAM with arbitrary data as well. First, a stream which boots SRAM cluster as well as a memory master in node 108 and wires in nodes 208 to 608 is built. The memory master is programmed to read a predefined number of words from node 208 and store them in RAM sequentially, starting from address 0. Code in wire nodes transfers the same number of words from boot node 708 to memory master. When the whole boot frame has been delivered, the boot node is instructed to read another frame. The next frame is built manually during compilation. Its transfer address points to the down port of node 708. The body of the frame contains the image bitmap to be stored in RAM. The body is delivered to node 608 and then propagates through wires to the memory master, which in turn stores data in RAM. Both wire nodes and memory master node are programmed to jump to the default reset address worm when the whole body of the frame has been delivered. Thus the chip is left in the same state as after loading SRAM cluster, with the difference that RAM has also been initialized. The same mechanism is used, for instance, in loading polyfourth nucleus, and this code is provided as a part of array4th source. Notice that nodes used as memory master and wires have booted, executed some useful code, and have finally been put back to their reset state so that they can be reused by application. This demonstrates that GA144 is a dynamic chip in the sense that its code can be modified many times and a particular node can perform different functions depending on the current needs of the application. Central part of the demo application performs convolution filtering. I will explain briefly how convolution filtering works and then describe how it has been implemented in this application. Convolution filtering is used for modifying the spatial frequency characteristics of an image. A filter applied to an image modifies pixel values in such a way as to enhance or suppress some features of the original image. Convolution filters are commonly used in bitmap editors to blur, soften or sharpen an image, to enhance or detect edges, to apply 3D effects such as embossing and so on. To explain the principle of convolution, let's have a bitmap whose top left corner is shown here. Each little square represents a single pixel. A convolution matrix or kernel is a square matrix with usually odd number of rows and columns, the simplest being a matrix of order 3. Each element of the matrix contains a factor which is assigned fractional number. Convolution is then a process by which the value of a pixel in the output image is calculated as a sum of products of the original pixel and its neighbors with the corresponding factors of the convolution kernel. This calculation is repeated for the whole bitmap. If we read pixels from the original image horizontally, we can visualize the kernel moving, for instance, left to right, descend one line at the end, and start over again. Convolution filtering usually requires values from pixels outside of the image boundaries. Techniques used include extension of border pixels outside the image boundaries, wrapping the image and taking values from the opposite edge, or cropping the image so that the output image is smaller than the original one. In our application, we use the simplest approach, which assumes that the pixels outside the image are all equal to 0. Before diving into details of how the convolution algorithm is implemented in our demo, let's summarize constraints imposed upon the application. The input image is a grayscale bitmap, 128 by 128 pixels large, 8 bits per pixel. The convolution kernel is a 3 by 3 elements matrix. As mentioned earlier, the out-of-image pixels are considered having zero intensity. The whole application has to be fast enough to be able to feed RGB video channels and stay in sync. This is the full application floor plan. Red arrows show flow of control signals, green arrows show flow of data. The application can be divided into several modules. There is a RAM reading module including SRAM cluster, a memory master in node 106, which reads sequentially pixel values from RAM, and two wire nodes. Since bitmap data are stored in RAM as 16-bit values, the memory master splits each value in 2 bytes and sends them downstream. When the full bitmap has been read, the master starts reading from the beginning again. Therefore, the image is continuously fed into the application. Next downstream module consists of 4 buffers, which are implemented as 2-port first-in first-out memory, each having capacity of 128 words. Each buffer holds pixel data for one bitmap line. At any given moment, 3 buffers are read by convolution kernel, while the 4th buffer is being filled with new data. Numbering the buffers from right to left, 4 reading sequences are used, specifically 1, 2, 3, 2, 3, 4, 3, 4, 1, and 4, 1, 2. The data ordering in the stream is ensured by buffer output gate nodes and distributor nodes, which feed the buffered data into the convolution kernel. Thus, kernel receives 3 consecutive bitmap lines simultaneously from left to right edge of the image. The kernel reads individual pixel values, performs calculations, and sends partial convolutional results downstream into 3 nodes that sum the results up and clip the final result to an 8-bit value, as some kernels produce results outside of the 8-bit scale. The processed pixel values are temporarily stored in another set of buffers. The reason for implementing those video buffers is that in order to enlarge the resulting image on VGA screen, the application displays each bitmap line with 3 scan lines. Therefore, one buffer holds a line just being displayed, while the other buffer is being pre-filled with the next bitmap line. The output of those buffers is passed by wire nodes to the last module of the application, VGA display module. As the demo application works with monochromatic images only, it is sufficient to implement only one VGA color channel and feed RGB lines from that one channel only. Although GA144 is an asynchronous chip, we need to synchronize data flow with an external device, this is with the VGA display. This synchronization is achieved with a clock module. Due to its size, I am not going to provide detailed description of the whole application code. Instead, in the following section, I would like to focus on 3 modules that utilize useful or interesting approaches and programming techniques. I will talk about input buffers, convolution kernel, and VGA display module. When talking about ports, I will use port names right, down, left, and up when referring to a particular port. However, to make it more comprehensible for those not accustomed to GA144 layout, I will use cardinal directions when referring to directions in general. Input buffer code will be demonstrated on a buffer made of nodes 4, 104, and 204. Other 3 buffers use the same code. Nodes 104 and 204 hold no code in their RAM as the memory is used for data only. The nodes put up suspended with the return stack fully pre-filled with value 63, register A initialized to 0, and register B pointing to up port. This is the port shared by both nodes. The nodes are waiting for code to be executed at their south ports. The node 4 boots up with register A pointing to the right port. This is to the node 5, where the data come from, and execution starts at word go. The first word to be executed is fill, which is responsible for filling 128 words into RAM of nodes 104 and 204. Let's delve into details of word fill. Since port execution is extensively used, it is helpful to distinguish code executed by the node the code is compiled for from code executed elsewhere. Coincidentally, array4th compiler, when compiling F18 code, does not make any difference between green and yellow words. For that reason, we can use green or yellow words interchangeably. We employ this fact here using green words for code that will be executed in node 4 and yellow words for code to be executed at ports of nodes 104 and 204. Another feature of the presented code is a repeated use of fragment fetch_p store_b ... This piece of code starts at a word boundary and occupies one instruction word. We need to use a dot, which translates into no operation, in order to always align the compiled code to word boundary. When executed, the code reads the following word from node's RAM and stores it where register B is pointing. Since register B has been initialized at the beginning of word fill to point to down port, words read by this fragment are sent to node 104. Now we can have a look at what word fill does when executed. First, fetch p store b ... is sent to node 104, which effectively converts this node into a wire node ready to pass one word where its register B is pointing to. This is to the node 204. Next, the word begin fetch p store plus micronext dot is sent from node 4 and passed to the up port of node 204 where it gets executed. This code is a micronext loop reading words from the same port where it is executing and storing them consecutively in RAM. Keep in mind that the return stack of node 204 is filled with values 63. The micronext loop takes its parameter from return stack. Thus, 64 words would be stored in RAM before node 204 suspends, waiting for another instruction word. However, for the time being, the node just expects this first word to be written to the port. Next word sent to node 104 is begin fetch p store b micronext dot. This makes again a wire node out of node 104, this time transferring 64 words to node 204. At this moment, both 104 and 204 are ready to receive 64 words and store them in RAM of node 204. This is achieved with the following code, which reads words coming from node 5 and sends them downstream. The execution continues, creating a one-word wire from node 104 again and sending jump to down port instruction to node 204. This instructs the node 204 to expect next instructions from its down port. This is from node 304. This way we have switched access to the buffer and data may be read from the buffer by node 304. The following code word sent to and executed by node 104 reads 64 words and stores them in RAM of 104. The data are again provided by reading from node 5. Finally, node 104 receives the last instruction word, a jump to up port, thus expecting to get next instruction word from the north. To sum it up, the word fill reads 128 words of data from node 5 and stores them consecutively in RAM of nodes 204 and 104. It is worth to note that A register, which is used as pointer in both 104 and 204, is left with value 64 when the buffer is full. Due to rollover of address pointer in F18 computer, this address actually points to location 0 in RAM. This is to the first data word stored there. The execution then returns to word go, where B register is loaded with left port address, and word pass is called 3 times, each time moving 128 words of data westwards from node 5 to fill other 3 buffers. The whole process is repeated indefinitely. The convolution matrix is defined in 9 nodes in a square between 602 and 404. For each column of the kernel, the code is the same. Image data are fed into the matrix in the eastward direction, 3 lines at a time. The core word of the kernel is star.r, which carries out multiplication of fractional and integer numbers. This word expects a fractional number in register S and an integer in register T. After multiplying those numbers, the fraction stays in S and an integer product is in T. The word takes into account value of the highest non-significant bit of the result and rounds the integer high if the bit is set. The format of the fractional factor is following. The most significant bit is a sign bit. Next 3 bits define an integer part of the number, and the remaining 14 bits define fractional part. Factors are therefore numbers defined in the interval from -8 to 8 exclusive. This interval has been chosen with respect to convolution filters used, as will be shown later. Data flow rate is a critical parameter for the convolution module. Since all 3 lines of the matrix execute the same code, I will demonstrate the approach used on the bottom line of the matrix. As explained earlier, pixel values to be convoluted are shifted into the matrix eastward, and in each step a multiplication of the pixel value and the corresponding convolution factor is carried out. Thus, we have 2 streams of data. The first one moves pixel values into the matrix. The second stream moves partial products out of the matrix. A word that takes care of coordinating those 2 intertwined streams is MAC. The word MAC is called from a loop defined in word go after a new pixel value has been read from the appropriate west port. Notice that pixel values provided to node 402 come from the distributor module, while those provided to nodes 403 and 404 come from the preceding nodes of the convolution matrix. The word MAC is slightly different for each column of the matrix. In node 402, it duplicates the current pixel value, stores it on the return stack temporarily, and carries out the multiplication step. The node then suspends due to its attempt to send the product eastward. Meanwhile, the word MAC in node 403 duplicates the current pixel value, stores it on the return stack temporarily, and carries out the multiplication step using its convolution factor. It then reads a value from 402, which is the result of multiplication, and adds it to its own product. It then attempts to send the sum of products eastward and suspends. Finally, the word MAC in node 404 performs multiplication, reads a value from node 403, this is a sum of products from the 2 preceding nodes, adds it to its own product, and the final sum is sent eastward. The value sent is a partial sum of products for the particular line of the convolution matrix. Note that the code in node 403 can now continue by sending a pixel value to the node 404, where it is read by the word go. Similarly, node 402 continues by sending its pixel value to node 403. This ends the word MAC in node 402, which returns to the word go, reads a new pixel value, and the whole process starts all over again. The rest of kernel code takes care of the right number of pixels processed and of setting 0 values when convolving pixels at the edge of image. All 3 lines of the convolution matrix perform the same calculations at the same time. Line results are summed up in a node 605 to 405, and the final result is clipped to 8 bits. This is a negative result is set to 0, and a positive result greater than 255 is set to this value. The display module is composed of 3 nodes. It receives 8-bit pixel values, converts them to analog voltage, and sets the analog output pin in sync with pixel gating signal. Analog output is provided by DAC in node 717. To set voltage on the analog output pin, we write a 9-bit value into I/O register. Due to the chip design, the value has to be exclusive ORed with a mask first. The voltage is set immediately following the write instruction. In order to set the voltage in sync with pixel gating signal, we have to use another feature of DAC node. Node 717 has a virtual pin shared with pin in node 715. Node 717 can read the level on this pin, which receives pixel gating signal from clock generator in node 300, and suspend until the level on the pin changes its value from that preset in wake-up direction bit of I/O register. Basically, if wake-up bit is set to 0, the node suspends while the pin is low and vice versa. The clock generator used for synchronizing data flow with the VGA display is similar to that presented by Chuck Moore at 4th Day 2012. Briefly, a 10 MHz ceramic resonator is connected between a GPIO pin of node 500 and the ground. This node drives the resonator and generates a clock signal that is fed through node 400 to node 300. Here a 5 MHz pixel gating signal is derived and output to pin 301. At each edge of the gating signal, 1 pixel is displayed. The composite video sync signal is output to pin 317, which is connected to VGA horizontal sync line. Timing is set in such a way that we get 640 by 400 resolution at 53 Hz refresh rate. This setting provides pixels with aspect ratio close to 1. It should be mentioned that not all VGA displays accept composite sync signal, but most modern do. The procedure for synchronizing analog output with clock is following. First, the stack of node 717 is pre-filled with alternating masks when the node is booted. These two numbers contain an exclusive OR mask 155 hex and alternating 0 and 1 wake-up direction bit. Word DAC expects a value for conversion on top of stack. It first exclusive ORs it with a mask, duplicates it, and stores the duplicate to up port. When we write into up port in an analog node, the value written has no meaning. The only effect is that the node suspends according to wake-up direction bit and continues when level on the shared pin has changed. Out of reset, wake-up direction bit is 0, so we wait until there is a high level on the shared pin. After wake-up due to level change on the shared pin, the node immediately stores the top of stack into I/O register, which sets DAC to a new voltage, and at the same time flips wake-up direction bit, so when we next time write into up port, the node will suspend until the level on the shared pin changes to low again. This code is repeated for every pixel displayed on the screen. The last thing to solve is how to get the pixel value on the stack of 717. We know that the value is provided by node 617, therefore we need to read down port. However, both registers A and B suitable for addressing are already used. We may use, for example, A register, load down port address into it, read a new value, and then load the register with up port address again. Though functionally correct, it is waste of time and energy, and for high pixel clock rates it might be too slow, so we would be out of sync quickly. Fortunately, there is another way to solve the issue. It is no surprise we will use port execution once again. In node 617 we define word feed, which expects a pixel value on stack. We first read yellow instruction word fetch p DAC ... and send it with store B to down port of 717 for execution. By this instruction, word reads the same port it is executing at, and what it reads is a pixel value provided by 617 with another instruction store B. With the pixel value on stack of 717, the execution continues by calling DAC, which we have already discussed. Notice that execution returns from word DAC back to down port. This is also why node 717 starts execution at down port as directed by its boot descriptor. The rest of code in node 617 takes care of reading appropriate values from 517 and providing them to DAC in 717, or sending 0 value to DAC when unused part of VGA screen is being displayed. It is worth noting that since definitions of code for both 717 and 617 use the same namespace, we can use word DAC in definition of 617 code, even if the word itself has been defined for node 717. Node 517 performs a simple scaling of pixel values. Scaling is necessary in order to convert 8-bit pixel values into 9-bit values accepted by DAC in Node 717 in such a way as to get the maximum of 0.7 volt analog output for the highest possible pixel value. This is for 255. Since DAC is a current source, its voltage is dependent on the load resistor used. Standard VGA monitors have termination resistors of 75 ohms. Empirically found value for DAC to set 0.7 volt on the analog output is about 200. However, we have attached all three analog VGA lines to the same DAC and therefore have three 75 ohm resistors in parallel, which gives load resistance of 25 ohms only. For such a configuration, 0.7 volt can be achieved with DAC value of 511. This is the top of DAC range. The scaling factor is thus 2 and the pixel value is simply left shifted by 1 bit. In order to run the application, we have to specify the image to be processed using word named, which is a standard array fourth word. Convolution factors have to be also specified as a part of boot descriptors of the nodes forming convolution matrix. We use colorforce scripts that simplify this task. Finally, the full application is compiled and loaded into the eval board. This picture shows the actual hardware used to run the demo application. The eval board has been fitted with a VGA female straight connector and a 10 MHz ceramic resonator. You can also see pixel gating signal between pins 301 and 715/17, as well as composite sync and analog signals. In the final part of the presentation, I will show some results generated by the application. You will see an original image, a convolution kernel used, and a camera snapshot of the actual result being displayed on a 14-inch VGA display. The first example is an image with an identity convolution filter applied. As you can see, the result is basically a copy of the original image. A blur filter applied to an image can be seen in the next example. Another example shows how the original image has been modified with embossing filter. The last example shows the result of applying edge detection filter to the image. My thanks go to Green Arrays for providing me with an evaluation board to develop this demo application and for helpful and valuable discussions. I would particularly like to thank Chuck Moore for showing how to control a VGA display from eval board and for many arithmetic examples coded in colorforth I used in my application. Pictures for this demo come from public domain pictures database and from author's archive. The presentation has been created with Movely, a cloud-based digital media and content creation software platform. Thank you for your attention.